Hello everyone, welcome back to the CS184 discussion recordings. Today we're going to do a little bit of an introduction to the math that's used in this course, so a little bit of linear algebra and then some random variables and probability. So let's start off with vectors, the most basic part of linear algebra. So vectors are lists of numbers or variables, and they can be any length, and we generally write them as vertical arrays like you can see with v and u. So v is a three-dimensional vector and u is a four-dimensional vector. And so two vectors are equal if they have the same length and the same values at the same spots. And typically in graphics, we'll use vectors for position on an image, which would be a 2D vector, a position in a scene or direction, which would be 3D, and for 3D vectors, typically it would be x, y, z in terms of elements. And we also use vectors sometimes for RGB, so another 3D vector. So let's talk about some operations with vectors. So some of the most basic operations are addition and subtraction. So addition, you can add two vectors as long as they're the same size, and it's an element-wide as addition. So 1 plus 4 equals 5, 2 plus 2 equals 4, so on and so forth, and that's how you add the vectors. And vector addition has a few key properties. So it's commutative, so a plus b is equal to b plus a, and it's associative, so a plus b plus c is equal to a plus b plus c, and addition with the zero vector, just like normal numbers. And so subtraction works quite similarly. It's just that instead of element-wise addition, it's subtraction, so 7 minus 4 is 3, 2 minus 3 is negative 1, so on and so forth. So if we come up here, there's a little bit of a diagram to kind of help you visualize addition and get a more intuitive understanding. So of these two vectors here on the bottom left, I'm going to label this one A and this one B. And so if we come over here to the axes, that right there is A and that right there is B. And so now if we wanted to find A plus B, that would be this red vector on the bottom. And if you think about why, you can think about, in this case, A and B are both 2D vectors. So the x component of A plus the x component of B is the x component of that red vector. And similarly, the y component of A plus the y component of B is the y component of the red vector. So this is basically visually element-wise addition. So this is A plus B. Okay, and so now we want to visualize subtraction also. And so if we think about it, A minus B is really the same thing as A plus minus B. So what we can do here, and that's this yellow vector, is we could negate each of the elements of B. So negate the x, negate the y, and we get minus B here in yellow. And so this top red vector is, we've done the same thing we did down here for A plus B, except now it's A and minus B. So this is A minus B. And so that's the same, element-wise subtraction. And so, and you can do the same in 3D and 4D and so on and so forth. It just becomes much harder to visualize. So I think 2D is a great place to make sure you have that intuitive understanding. Okay, so that's addition and subtraction. Another pretty key property is the length of the 3D vector. So the length of the vector is this formula right here. And if you look at it, it probably looks somewhat similar to the Pythagorean theorem, and that's because it really is. So if we look at this drawing up here, the length of the vector L is, there's x and there's y, and they form a right triangle. So we would write L squared is equal to x squared plus y squared. And then, take the square root of both sides, and we get L is equal to the square root of x squared plus y squared. And that's essentially exactly what the length formula is, just generalized to 3D. And so the length is often written like this with two vertical bars on the side of the vector. And any vector with length 1 is called a unit vector. And so these are used relatively often in graphics. So oftentimes you'll be asked to normalize a vector. And the way you do that is by taking the vector and then dividing every element by its length, which will normalize it to 1. Okay, so one of the next key properties of vectors, something important to know, is the inner product or the dot product. It's more commonly referred to as the dot product, so keep that in mind. And basically, it's quite simple. It's a scalar quantity, not a vector, And all it is the sum of element-wise multiplication, essentially. So if we have vectors a and b, it's a1, b1, so first element of a times first element of b plus second element of a times second element of b, all the way, sum it all up, and the answer you get is the dot product. Okay, and so the dot product has a few nice properties similar to addition. So one of these properties is a dot b is equal to b dot a, so it is commutative, just like addition. And similarly, we could also write a dot b plus c is equal to a dot b plus a dot c. So you can kind of just distribute the dot product. Okay, and so another really useful part of the dot product is that we can use it to get information about the angle between two vectors. And this angle is often used in graphics. It's quite important. So the dot product is also used a lot. And so the formula to do that is this one right here. And it says cosine theta is equal to the dot product of a and b divided by the magnitude of a times the magnitude of b. And so that's just a formula, good to remember, good to keep in mind. But so one thing kind of that we can glean from this is that when cosine of theta is equal to 0, then the dot product of a and b must be 0, because the magnitudes cannot, like the denominator cannot be 0 in this. That would just, cause problems. So, and when the cosine of theta is 0, that means theta is 90 degrees right there. So essentially what that's telling us is when the dot product of two vectors is 0, that means they have a 90-degree angle between them. So they are perpendicular vectors. So this can be quite important. So that's always a good thing to keep in mind. When the dot product of two vectors is 0, they're perpendicular. Okay. So speaking of perpendicular vectors, we come to the cross product. So the cross product of two vectors, it's a new vector that is perpendicular to both of the original vectors. And so this cross product only exists in 3D. And so here's the equation right here. I don't know if you need to memorize it, but it could be a good idea. So it's just, a cross b is a2b3 minus a3b2. I'm not going to read it out, but it's right there. You can find it easily if you Google it online. So one of the issues, I guess, not really an issue, but one of the things with the cross product to keep in mind is that for any two vectors, there are typically two vectors that are perpendicular to both of them. So you have to know which one the cross product is going to give you out. And so what the cross product does is it follows the right hand rule, which says that if you curl the fingers of your hand from A to B, your thumb will point in the direction of the cross product. So if we look at this diagram that I've drawn here on the right, I've labeled A and B. And so if our fingers curl in this direction, the vector drawn is the one that we'll get back. And so that's just a kind of a simple visualization of the cross product, but remember the right hand rule to make sure you're getting the vector out of a cross product that you expect. Okay, so now that we've learned some of these properties, let's go ahead and do a practice problem with these. So, it's just a plus b minus the cross product of a and b, all of that dot b. So let's go ahead and just try it. We can start with a plus b. So a plus b is equal to, and so it's element-wise addition, so it's 7 plus 1, 8, 2 plus 6, 8, and then 5 plus 1, 6. Okay, so there we go. That's a plus b. And now we want to get a cross b. And so I'm going to do it up here because I don't have a lot of space, unfortunately. A cross b. So let's just go ahead and follow the formula. So a2 times b3, so that's 2 times 1, so 2, minus a3 times b2, so 5 times 6, so 30. So 2 minus 30. A3b1, so 5 times 1, so 5, minus a1b3, so 7 times 1, so 7. And then a1b2, so that's 7 times 6, 42, minus a2b1, so 2 times 1, 2. Okay, and so if I write this down here, that's going to be negative 28 -2, and 40. Okay, so that is A cross B. So now that we have A plus B and A cross B, let's go ahead and subtract. So what we're going to want is 886 minus -28, -240. And so if we just go ahead element wise, so that's going to be 8 minus 28, so that's 36. 8 minus -2, so that's 10. And then 6 minus 40, so that's -34. Okay, and now what we want to do is take the dot product of that with B, which is 1, 6, 1. And so if we write this out, what we're going to get is 36 times 1, so 36, plus 60, 6 times 10, so 60, minus 34 times 1, so 34. And so if we solve this out, 36 minus 34 is 2, so 62. And that is our answer. Okay, so nothing too complicated, basically just following the steps exactly, follow the cross product equation, and we get the answer. Okay, so let's keep going. So next up are matrices. And matrices are essentially two-dimensional arrays of numbers. And so you can also think of them kind of as a stack of vectors where each column or each row is a vector. And so in this case, we have, example matrix M, which is a 2x3 matrix. So now, one of the big properties of matrix multiplication, of matrices is matrix multiplication. And so we can multiply an m by n array with an n by k array to get a new array of size m by k. So that can be kind of confusing at first, so we can go ahead and walk through it. So, and the value of the result is essentially the dot product of the value in the ith row and jth column of the resulting matrix is the dot product of the ith row of A and the jth column of B. So this can all be kind of confusing, but we'll go ahead and walk through it. So first, let's look at the dimensions. So of this problem we have here, this matrix on the left is it has 2 rows and 3 columns. So it's a 2x3 matrix. Okay, so I'll just write that there, 2x3. And then we're multiplying that, I'll put a little asterisk, okay? And we're multiplying that by, this is 3 rows and 2 columns. So we're multiplying that by a 3x2 matrix. And what we get out is 2 rows and 2 columns. So essentially, the way matrix multiplication works is it takes the number of rows of the first matrix and the number of columns of the second, and that's the dimensions of your result. So 2, 2, and you get a 2x2 matrix out. Okay? So now that we have that, let's look at how to actually compute the values. So all this is essentially right here where we have 81. That's in the first row, first column. And so what that's going to be is, it's going to be the dot product of 157 with 894. So let me get rid of that. So the dot product of 157 with 894 is 81. And then for 55, it's in still the first row, but the second column. So we're going to take still the first row, so 157, dot product with the second column, so 326, and we'll get 55. Same with 73, so second row, first column, so we're going to take 253, dot product with 894, 73. And for 34, we're going to get 253, dot product with 326, and that's how we get 34. So matrix multiplication is essentially just a series of dot products, and that's all. Matrix multiplication is not commutative, so A times B is not the same thing as B times A. So that's an important thing to keep in mind. And so multiplying by a vector, multiplying a matrix by a vector is essentially just an extension of this. And so actually we can go ahead and do a quick problem. So if we go maybe 2, 1, 3, 1, and let's say 1, 2, just a very simple. And so first off, let's look at the dimensions. So this is a 2x2 matrix multiplied by 2 rows, 1 column. So it's going to be 2 rows, 1 column. And so here I can just write it out to make it clear. So 2 by 2, 2 by 1. So we're going to take that dimension and that dimension. Okay, And so now let's look at the actual answer. So we're going to go 2, 1, the dot product of 2, 1 with 1, 2. So that's going to be 2 times 2, so 2 plus 2, so that's 4. And then 3 times 1 plus 2 times 1, so that's going to be 5. And so there we go. That's our answer. So just like matrix multiplication, it's matrix vector multiplication. Okay, let's keep going. So another key property is inverses. So the inverse of a matrix, so it's generally written like this with a -1. And it's a matrix such that A times its inverse is equal to its inverse times A. So in this case, it's commutative. And the multiplication is always equal to I, where I is the identity matrix. So the identity matrix looks something like this in the 2 by 2 case. Just like that, and you can kind of extrapolate, but always has 1s on the diagonal and 0s everywhere else. And if you, this is something to test at home, but if you multiply any matrix by the identity matrix, it stays the same. So try that out yourself, prove that to yourself. So using inverses, essentially, we can now start to solve equations of matrices. So in this case, we have C is equal to AB. And so if we multiply both sides by the inverse of A, we'll get inverse of A times C is equal to just B. But one thing to keep in mind, though, is only square matrices with non-zero determinants have inverses. We haven't really talked about determinants, so don't really worry about that, but just do keep in mind that in order for a matrix to have an inverse, it must be a square matrix. But okay, not all square matrices have inverses. So for example, this example right here, 0, 0, 0, 1, is a square matrix, but is not invertible. Okay, so let's try out some problems with inverses just to get some practice. So A is equal to this matrix right here, 1, 2, 3, 4. And let's try to find a 2 by 2 matrix that commutes. So AB is equal to BA. So, well, trivially, we can come up with a solution, and that's 0, 0, 0, 0, right? So no matter what way you're multiplying this, everything you get out is just going to be zeros. So A times B, all zeros, B times A, all zeros, and that works. Okay? And now let's come up with a 2 by 2 matrix that doesn't commute with A. So this is easier because there's just a ton of options. So, I mean, we could even just do 1, 1, 1, 1, right? And so let's try this out. Let's make sure that it doesn't commute, right? So say this is B, right? So let's go. AB is equal to 1, 2, 3, 4 times 1, 1, 1, 1. So if you want to pause, get some practice with matrix multiplication, now's a great time. But let's go ahead. So that's 3, also 3. Then this is going to be 7 and 7. Essentially, we're just summing up the rows of A. And then now let's do it the other way. So BA is equal to 1, 1, 1, 1 times 1, 2, 3, 4. And that is going to be equal to, so it's a 4, 6, 4, 6. Okay, so clearly these are not the same. 3, 3, 7, 7, 4, 6, 4, 6. So there we go. B is a matrix that does not commute with A. Okay, so simple enough. Let's keep going. So the 2 by 2 matrix C. Now we want to find the 2 by 2 matrix C that satisfies A times C is equal to the inverse of A. And so thankfully we've been given the inverse of A here, so we don't have to worry about computing it. So, well, let's look at this problem, right? It reminds me of something we talked about right here, where we have C equals AB, multiply both sides by the inverse. So in this case, if we have AC is equal to A inverse, what if we were to multiply this by A inverse and this by A inverse? And so this cancels out into the identity matrix, which we can basically assume isn't there because multiplying something by the identity matrix doesn't change it. So it's basically gone. So C is equal to inverse of A times inverse of A. Okay, so let's go ahead and do the calculation. So we want -2, 1, 3, 2, -1 half, and then -2, 1, 3 over 2, -1 half. Okay, so once again, another opportunity to pause, practice some matrix multiplication, but let's keep going. So -2 times -2, so 4 plus 3 over 2. So that's going to be 8 over 2 plus 3 over 2, so 11 over 2. And then -2 times 1, so -2 minus 1 half. So it's going to be -4 over 2 minus 1 over 2, so that's -5 over 2. Then down here, so we have -2 times 3 halves, so that's -6 over 2. And then -1 half times 3 halves, so that's going to be -3 fourths. So if we convert -6 over 2, that's -12 over 4, minus 3 fourths, so that's -15 over 4. Oops, okay. And then last one, so that's 3 halves plus 1 fourth, so that's going to be 6 over 4 plus 1 fourth, so that's going to be 7 over 4. And so there we go. That's equal to C. Okay, so here I can put C is equal to that. Okay, so that's how inverses work. They're a useful tool for solving equations involving matrices. Okay, let's keep going. So now we're going to switch gears a little bit and talk about random variables, which is another math topic we use in the course, which comes up a little later. So a random variable represents basically a quantity which we don't know, but it could take up any number of values, and each value has some probability assigned with it, some chance of happening. So for example, variable x here is the result of rolling a dice. So if we look at this table on the left, we see that the outcomes are 1, 2, 3, 4, 5, 6, and each of them has a 1/6 probability, so 1 in 6 chance that you'll roll that number. And then y on the right here is the number of heads we get when flipping a coin twice. So here we can get 0 heads, which are both tails, 1, which is 1 head, and then 2, so we get heads on both. So it's 1/4 for 0 because it would have to be tails, which is 1 half, times tails, which is another half. And similar for 2 because it would be heads times heads, so 1 half times 1 half, or 1/4. And then for 1, it could be tails, heads, or heads, tails. So that's why it's 1 half, that has double the probability. So these are both examples of discrete random variables. So random variables that can only take a set number of values on. So, in x it's 6, in y it's 3. So it's very easy for us to write out the probability like we did here. But suppose we have a variable z, which is the exact amount of rainfall we'll get tomorrow in inches. So z could take on an infinite number of values, right? So there's no way we could go ahead and make a table like this and write out all the probabilities. So instead what we do is we talk about ranges. So we'll have something called a probability density function, or a PDF, which we talk about right down here. And so it represents a probability associated with the range. So in this case, suppose we want to find the probability between some z0 and z1. Then what we do is we take the integral of that probability function, which tells us hypothetically at exactly every point what is the probability. So we sum up all of those, and that's the probability of it being anywhere in that region. So as an example, let's take this example probability density function. So that's it's 3 times x minus 1 squared if x is between 0 and 1, otherwise it's 0. Okay, and so if we want to find the probability of getting between less than half, if we want to find the probability of less than half an inch of rain tomorrow, what we do is we integrate from 0 to half of this probability density function. So plug it in, we take the antiderivative, plug it in, solve, and we'd find that it's 0.875. So there's an 87.5% chance that we have less than half an inch of rain tomorrow. And so we could also do this for, let's say, what's the chance we get between 1 and 2 inches? So if we do that, plug it in, 1 and 2. However, if we look at the definition of the probability density function, it's 0 everywhere outside of 0 to 1. So for 1 to 2, it's 0 everywhere. So we have no probability of getting between 1 and 2 inches of rain tomorrow. Okay, so there's a couple rules that probability density functions or PDFs have to satisfy. One of them is that they have to be non-negative, which is just because I don't think you can have a negative probability. I'm not sure what that would look like. And another thing is that it has to satisfy this integral, which is basically all it's saying is that the total probability across all possible outcomes has to be 1. So basically something has to happen. And so this is just another way of writing that. Basically you're taking the integral from negative infinity to infinity, so all numbers, and if you take that integral, the total probability has to be 1. And you could write a similar thing for discrete, where you would kind of sum up over all possible outcomes, and that probability has to be 1. Okay, so let's do some problems with this probability density functions to get an idea of it. So the amount of money you'll win in a game is given by a random variable m, which is, this symbol means it's drawn from the probability density function p of x. So, and we're given p of x, so it's 1 over x squared if x is greater than 1 and 0 otherwise. So we want the probability that you will win at least $2. Okay? So what we want is essentially, we want the integral from negative infinity to 2 of p of x dx, just like that. However, we know that p of x only has positive or any values other than 0 for x greater than 1. So we can change the lower bound of this integral. And so we can write 1 to 2, integral from 1 to 2 of p of x dx is the probability we're looking for. So if we go ahead, plug the actual function in, so it's 1 over x squared dx. And so we can go ahead and take the antiderivative, so that's 1 over x from infinity, oh, wait, no, sorry. Oh, my bad. We're doing this entirely wrong. This should be swapped. Sorry about that. So it's at least $2. So we're going 2 to infinity. So 2 to infinity, infinity to 2. Okay, there we go. So now this isn't super rigorous because of the infinity, there's some extra math we should do. But we could just think of that as 0. So it's going to become 0 minus negative 1/2. And so that's 1/2. And so that is the probability that we win at least $2. So we have a 50-50 chance. Okay, so that's kind of a brief introduction to just the integration idea. And so let's keep going. So now we have a random variable x, which is determined by the PDF p of x, where p of x is a over x cubed for x greater than b. So now we have two unknowns here. A and b are not given, but we know that they're positive real numbers. And there's a 1/4 chance that x will take on a value greater than 5. Okay, so let's think about how to do this. A value greater than 5 is kind of what we did last time, right? So we can essentially write that 1/4 is equal to the integral from 5 to infinity of p of x dx. So the integral from 5 to infinity of a over x cubed dx, which if we take the antiderivative, which I'm not going to spend time explaining, is still infinity to 5. And so if we plug this in, once again the infinity makes it go to 0, so it's going to be 0 minus negative a over 2 times 25, so 50. So it's going to be a over 50. Okay, so 1/4 is equal to a over 50. And so that means we're going to be able to go ahead and right here, write a is equal to 50 over 4. Okay, cool. So now one of the two unknowns, we have it. We've solved for it. And so now what we're going to do is we're going to use another property we just discussed, which is that the total probability, the integral from negative infinity to positive infinity, must be 1. So what we can write is 1 is equal to negative infinity to infinity p of x dx. However, we also know that for all x less than b, it's 0, so we can ignore those. And so what it's going to be is, and we know b is positive, so we can write b to infinity of p of x dx is equal to 1. So we can, once again, plug it in. I'm still going to leave the a in there to save myself from having to write numbers, but what we're going to get out basically is equal to, so the same thing is up here, we're going to get out. So it's going to become a over this 2 times this lower bound squared. So in this case, it's going to be 2b squared. Okay, and so now if I'm going to come back over here to the left side, sorry, I'm running out of some space, but so we know that, so we can write 2b squared is equal to a, and so b is equal to square root of a over 2, and if you plug in all the numbers and do the math, you'll get b is equal to 2.5. So that's this value right there. Sorry, I ran out of space on that. Okay, so here we used, first just the typical integral over a region to get the value of a, and then we used the property that the total probability has to be 1 to solve for b. Okay, so let's keep going. So the next topic is expected value, and the expected value is a pretty useful and oftenly used kind of property of a random variable. And so the expected value is the weighted average of its values, where the weights are given by the probability. So essentially, if we look at this equation right here, the expected value of x is the value of x times the probability that it is that. So x times probability that x is equal to x. And so we take the sum over all possible values. So this is a pretty intuitive idea. It's basically like, what number am I getting times how likely am I to get this? And we sum them all up, and that's the expected value. And so we can also write something similar for continuous random variables. Is just replace the summation with an integral. So expected value of z is the integral of z times the probability density function of z, dz. So another thing we want to do sometimes is apply functions to random variables. So we would want to get x squared, or z times 2.54, something like that. And so the way it works, and it's quite simple, or not simple, but quite intuitive, is the expected value of f of x, where f is whatever function we want to apply, is basically you just take x out of the equation and plug it in with f of x. So it's going to be the summation of f of x times the probability that x is equal to x. Notice that this x doesn't change. It stays the same. So, and this is also kind of intuitive. Basically, it's what's the new value through the function times the probability that I'd get the original value. And so similarly in the continuous case, we replace the summation with an integral. Okay? And so some important properties of the linearity of expectation is the linearity of expectation. And so here it is basically written out, is the expectation of c times x is equal to c times the expectation of x. So for example, up here when we said, the f of x could be z times 2.54, that's essentially just 2.54 times the expected value of z. And then the other one, which is also really important and we'll use in this class, is the linearity of expectation tells you that the expectation of a sum of random variables is the sum of their expectations, no matter what the relationship between them are. So expectation of x plus y is expectation of x plus expectation of y. And this is a really useful property that'll come up often, so keep that in mind. So let's go ahead and do some practice problems with expectation, just to kind of get some more practice with it. So the amount of money you'll win in a game is given by the random variable m, which is drawn from this probability density function p, where p of x is 1 over x squared if x is greater than 1 and 0 otherwise. So let's start by finding the expected value of the square root of m. So expected value of the square root of m is equal to, And if we come up here, we're basically using this, the continuous version. So we can go ahead, put an integral. Basically, just like before, we know that everything less than 1 is 0, so we can omit that. Just put there, and then that's a 1 over x squared times x. Remember, that's the equation, square root of x. And then dx, keep going. So basically, that's going to be x to the negative 3/2 from 1 to infinity. And if we take the antiderivative, we're going to get negative 2 x to the negative 1/2 from infinity to 1. And that's essentially going to be equal to, you put in the infinity, once again, we're going to get 0. And then so it's going to be minus negative 2. So that's 2. Okay. So the expected value of the square root of m, so the square root of the amount of money you're expected to make is 2. So now the next part is, why is it impossible to find the expectation of m? So let's just go ahead and try it. Let's try to find the expectation of m. So expectation of m, and this is even more straightforward because there's no function we're applying. It's similar setup. So integral from 1 to infinity of 1 over x squared, except this time it's not square root, it's just x. We can rewrite that as 1 to infinity of 1 over x. And there we go. That's the problem. So if you're not familiar with this, with the integral of 1 over x, it's a divergent integral. So essentially it goes to infinity. So this is infinity. So we can't find the expected value of m because it's infinitely large. Okay, so that is something that could happen. Okay, so that's some practice with the expected value equations. So let's do one more problem. And this is the last problem of the worksheet. So this is basically all the content we're introducing. So let x be a continuous random variable and let a and b be real numbers with a less than b. So find a function f such that the expectation of f of x is equal to the probability that x is between a and b. Okay, so I highly suggest you guys pause, try this on your own, and then see if you can come up with a function that works. But I'm going to go ahead and kind of give you guys an answer. So one possible function, and there are probably many, is, let's put f of x is equal to, we'll do a piecewise function just like we have before. We're going to put 1 if x is between a and b, and 0 otherwise. Okay, pretty simple function for f. So let's go ahead and try it. Let's make sure that this expected value is what we want it to be. So the expected value of f of x is equal to the integral from negative infinity to infinity of f of x times the probability of x dx, okay? And now by our definition, f of x is 0 everywhere outside of the region between a and b. So we can rewrite this integral as an integral from a to b, because we know that a is less than b. F of x, p of x, dx. And now also by our definition, we know that f of x is actually just 1 everywhere in this integral, in this region. So we can come down here. That's the integral from a to b of p of x dx. But if we look at this, this is exactly the equation we saw earlier for the probability of a range, right? If we come up all the way here, right, the probability that p of x is between 0, 0, and 0, 1 is the integral. So if we come back down, essentially this is the probability that x is between a and b. So there we go. It's done. That's a valid function. Okay, so that's all for today. I hope you all learned something and that this was useful. One of the other TAs is going to upload a brief C++ introduction soon, so look out for that. And that's all. See you next week.